A compressor network does not become stable merely because every individual controller is stable. That's the first principle you need to understand. When compressors operate in parallel or in series, the machines, drivers, recycle valves, process headers, piping volumes, and control loops form one dynamic system. If each controller acts independently, the result can be unequal loading, unnecessary recycling, pressure oscillation, excessive surge margin, unstable transitions, and, in the worst case, compressor surge. The real engineering objective is not simply to control pressure, flow, or speed. You must coordinate capacity control, load sharing, surge protection, and process override, so every action supports the complete compressor network. Let us begin with parallel compressors. A conventional strategy may fully load one compressor and throttle another. One machine can then approach its surge control line while the second still has unused capacity. The first compressor begins recycling, wasting energy and absorbing the entire disturbance, even though the second compressor could safely carry more load. Operating both machines at equal speed or equal flow does not necessarily solve the problem. Even nominally identical compressors can behave differently because of fouling, wear, seal leakage, manufacturing tolerances, gas composition, and internal clearances. Equal speed does not guarantee equal distance from surge. Equal flow does not guarantee equal aerodynamic risk. The correct variable to equalize is normally each compressor's relative proximity to surge. In a coordinated parallel compressor system, one station controller regulates the common process variable, such as suction pressure, discharge pressure, or header flow. Each compressor has its own load sharing or performance controller. Each compressor or compressor section also has its own anti-surge controller. These controllers have different responsibilities. The station controller determines how much total capacity the process requires. The load-sharing controllers determine how that capacity should be distributed between the operating machines. The anti-surge controllers determine the minimum internal flow required to protect each compressor. Primary capacity control begins at the station level. The station controller compares the measured process variable with its set point and calculates a PID response. That response represents the required change in total compressor network capacity. But this response must be applied through the correct final control element. When more throughput is required and the compressors are not recycling, the capacity demand should normally increase driver speed, inlet guide vane position, suction throttle position, or another performance control element. Opening recycle valves while demanding more throughput would be self-defeating. When less net throughput is required and the compressors are already near surge, further speed reduction may move them deeper toward instability. Under those conditions, the capacity response is applied through the anti-surge valves. Recycle flow increases, net process flow decreases, and minimum compressor flow remains protected. This automatic transfer of capacity action between performance control and recycle control is essential. The network must manipulate the element that satisfies the process demand without weakening surge protection. The next function is load balancing. Each anti-surge controller calculates a variable representing the operating point's distance from its surge control line. For a multi-section compressor, the section closest to surge governs the usable margin of the complete machine. The load-sharing controller therefore selects the most limiting section. The station controller receives the selected surge distance values from all operating compressors and calculates their average. Each compressor's load-sharing controller compares its own selected value with that average. A compressor operating farther from surge than the others can accept more load, so its performance demand is increased. A compressor operating closer to surge must surrender load, so its performance demand is reduced. These coordinated corrections continue until the machines operate at approximately equal relative distances from their respective surge control lines. This is the key point. You are not forcing equal speed. You are not forcing equal flow. You are not assuming identical compressor maps. You are distributing process load according to the actual aerodynamic capability of each operating machine. This prevents one compressor from recycling while another still has available stable capacity. It reduces energy loss, lowers recycle valve duty, and allows disturbances to be shared across the network. Primary capacity control and load balancing must also be separated conceptually. Primary capacity control raises or lowers the performance of the entire compressor network to restore station pressure or flow. Load balancing redistributes capacity between compressors while producing as little net change in total station output as possible. If one compressor is too close to surge, its load-sharing controller reduces its load. Another compressor operating farther from surge increases its load. Total network capacity remains approximately constant while internal loading is redistributed. Without this coordinated counteraction, every load-sharing correction would disturb the header pressure and force the station controller to correct that disturbance. The loops would start fighting each other. When recycling becomes unavoidable, a further problem appears. Recycle valves can open by significantly different amounts. One compressor may carry most of the recycle duty, while another remains only slightly open. Recycle balancing corrects this inequality. As the machines move towards surge, the controller demanding the highest recycle rate must retain unrestricted authority because it is protecting the most vulnerable machine. The other recycle controllers can then be moved gradually toward that highest recycle requirement. As the machines move away from surge, the most open recycle valve can close faster, while the others close more slowly. The demands converge without compromising protection. But balancing raw valve position is not enough. Equal valve position does not necessarily mean equal recycle flow. Actual recycle flow depends on valve characteristic, pressure differential, discharge pressure, suction pressure, temperature, gas properties, and recycle line resistance. A sound strategy therefore balances normalized recycle flow or recycle demand relative to each valve's available capacity, not merely valve position. Some parallel installations use individual hot recycle loops together with one common cold recycle loop. The hot recycle valves protect individual compressors during sudden disturbances. They act quickly but return hot discharge gas directly toward the suction system. Continuous hot recycling can therefore cause temperature buildup. The cold recycle circuit routes gas through a cooler before returning it to suction. For sustained recycling, the cold recycle valve should begin opening before the individual hot recycle valves. The cold path then carries the continuous recycle duty, limits temperature rise, and reduces the need for multiple recycle coolers. The hot recycle valves remain available for rapid local surge protection. The cold recycle valve manages the slower, sustained recycle requirement. This is an effective separation of fast protection from thermally stable, continuous operation. Now consider compressors operating in series. In a series train, essentially the same mass flow passes through each compressor, but each machine contributes part of the total pressure ratio. You therefore cannot distribute load simply by assigning different process flows. Load sharing must adjust speed, head, or compression ratio while respecting the surge condition of every compressor section. Far from surge, it may be reasonable to operate the compressors at equal speed or according to a selected compression ratio relationship. Near surge, that objective must change. The correct near surge objective is to keep all compressors at comparable relative distances from their surge control limits. Once recycling begins, the objective changes again. The system should equalize normalized recycle demand so one compressor does not move unnecessarily far away from surge while another remains heavily recycled. A useful series compressor load variable can therefore combine three quantities: the selected capacity variable, the proximity to surge, and the normalized recycle flow. Far from surge, the load variable is dominated by speed or compression ratio. As the train approaches surge, the influence of speed or compression ratio is progressively reduced and the influence of surge proximity is increased. At the surge control line, the load variable is dominated by surge proximity and recycle flow. This transition must be continuous. A sudden switch from speed balancing to surge distance balancing can create abrupt load transfer, driver movement, pressure disturbance, or recycle valve movement. A weighting factor can be calculated using the compressor currently closest to surge. Below the first threshold, the load function depends mainly on speed or compression ratio. Between the first and second thresholds, it becomes a weighted combination of the selected capacity variable and surge proximity. Beyond the second threshold, it depends mainly on surge proximity and normalized recycle flow. The load-sharing controllers then drive each compressor's load value toward the average value for the train. Suppose one compressor in a series train has a load value below the average while the train is near surge. Its load-sharing controller increases that compressor's performance. The machine moves closer to its surge control line. If recycle is already active, its anti-surge controller opens the recycle valve further, increasing its normalized recycle contribution. If another compressor has a load value above the average, its performance is reduced. It moves farther from surge, its recycle demand decreases, and its load value falls toward the average. At the same time, the station controller adjusts the total train performance to restore the required process pressure or flow. The result is a coordinated two-level action. Local controllers redistribute pressure-producing duty between machines. The station controller maintains total train duty. This is particularly important in series trains because the machines are strongly coupled. Increasing the speed of one compressor changes its discharge pressure, the suction condition of the downstream compressor, the total train pressure ratio, and potentially the operating point of every section. A load-sharing correction applied to one machine is therefore not a local event. It propagates through the entire train. Now we reach one of the most common causes of unstable compressor operation: control loop interaction. Every dynamic compressor normally has at least two major control objectives. The performance controller regulates pressure, flow, temperature, or another process variable. The anti-surge controller protects the compressor by manipulating recycle flow. These controllers affect the same process through different paths. The performance controller changes compressor capacity. The anti-surge controller changes internal flow. Both actions influence suction pressure, discharge pressure, compressor flow, and operating point location. Consider a compressor controlling suction pressure through driver speed. An upstream disturbance reduces process flow. The pressure controller responds by reducing speed, but the reduced speed may decrease compressor flow further and move the operating point closer to surge. The anti-surge controller responds by opening the recycle valve. However, the recycle system contains valve stroking time, piping volume, gas transport delay, cooler volume, and compressor response delay. The additional recycle flow does not reach the compressor immediately. During this delay, opening the recycle valve can temporarily worsen the pressure error. The pressure controller then makes another speed correction. The anti-surge controller makes another recycle correction. Their effects arrive at different times and with different gains. The loops begin hunting. One controller tries to restore process performance. The other tries to preserve aerodynamic stability. Both controllers are individually correct, but together they produce unstable behavior. A common response is to detune the controllers. This may reduce oscillation, but it also makes pressure control sluggish and surge protection less effective. The better solution is dynamic decoupling. Decoupling means that when one controller makes a known move, a compensating signal is sent to the interacting controller or performance element. The system anticipates the interaction instead of waiting for the process variable to deviate. For example, when the anti-surge controller begins opening the recycle valve, the decoupling algorithm can simultaneously increase compressor speed. The speed increase produces an immediate rise in compressor flow, while recycle gas is still traveling through the piping network. Once the recycle flow reaches the compressor suction, the temporary speed correction can decay or be absorbed into normal capacity control. This does not override the anti-surge controller. It strengthens the initial protective action. In high-volume recycle systems, the delay between valve movement and increased compressor flow can be several seconds. Effective decoupling can reduce the initial response time dramatically by creating a faster parallel correction through speed. That difference can determine whether the compressor remains stable or crosses the surge limit before recycle becomes effective. Dead time cannot be corrected simply by increasing proportional gain. Aggressive gain applied to a delayed process usually increases oscillation. You must reduce the physical delay, provide a faster corrective path, or predict the delayed effect and compensate for it. Effective decoupling requires the correct direction, magnitude, and dynamic duration. Too little compensation leaves the interaction unresolved. Too much compensation creates a new disturbance. A permanent compensation for a temporary interaction creates bias. A compensation that decays too early provides insufficient protection. The decoupling model must therefore reflect the real dynamics of the driver, compressor, valve actuator, recycle piping, and process volume. Another essential layer is pressure override control. Normal PID capacity control is designed for routine regulation. It may not respond quickly enough to a large or rapidly developing pressure excursion. Pressure override provides an additional one-sided response. For discharge pressure or net flow control, it acts when the variable rises too high or too rapidly. For suction pressure control, it acts when the variable falls too low or too rapidly. The override can contain two components. The first responds to excessive deviation beyond a defined limit. The second responds to excessive rate of change by comparing the instantaneous process value with a filtered value. This is important because a process variable may still be inside its absolute limit while moving toward that limit dangerously fast. The predictive term detects the trajectory and initiates corrective recycle action before the final limit is crossed. The override demand is sent to the anti-surge controllers. Each anti-surge controller compares the override demand with its own surge protection demand and applies whichever requires more recycle. This high selection principle is critical. Pressure override may increase recycle above the immediate surge requirement, but it must never close the recycle valve below the position required for surge protection. When you design or review a compressor load sharing system, do not begin with PID tuning. Begin with control authority. Identify which controller owns the station pressure or flow. Define how total capacity demand is distributed. Define how each machine's limiting surge section is selected. Define the load balancing variable. Define the transition from normal capacity sharing to surge distance balancing, and then to recycle balancing. Confirm how the system behaves when a transmitter fails, a compressor trips, a driver reaches its limit, a recycle valve saturates, or one machine changes operating mode. Check whether the load sharing calculation uses valid aerodynamic variables or convenient but misleading substitutes. Verify consistent engineering units, scaling, sign conventions, execution rates, and signal quality. Examine the actual recycle loop delay. Include actuator response, valve stroking time, piping volume, cooler volume, gas transport time, and compressor response. Test the complete compressor network dynamically. A stable compressor controller tested in isolation does not prove that the integrated station will be stable. The final lesson is simple. Good compressor control is not about making every loop faster. It is about making every loop coherent. Primary capacity control must satisfy the process. Load balancing must distribute aerodynamic duty. Anti-surge control must remain authoritative. Recycle balancing must minimize unequal waste. Cold recycle must manage sustained thermal duty. Pressure override must intercept dangerous process excursions. Loop decoupling must prevent controllers from fighting and compensate for dead time. When these functions are coordinated, the compressor network behaves as one controlled system. Pressure becomes steadier, recycle decreases, energy consumption improves, surge margin is used more intelligently. Disturbances are shared instead of being imposed on the weakest machine. That is the difference between controlling several compressors and controlling a compressor network.